In this video, we are going to discuss stars and bars, which is a pictorial diagram that pops up in studying certain counting problems. So we'll see a variety of different counting problems and see how stars and bars solves them. Problem 1. Consider the problem distributing 7 stars to 3, well, let's say ninjas. Right? Throwing stars, for instance. Well, the idea behind this problem is that you can't distinguish between different throwing stars, so they're identical objects, but supposedly you could distinguish between the 3 ninjas. So one way to draw the diagram is to, well, give 3 stars to the first ninja, or 2 stars to the second, and 2 stars to the third. Or you could consider other possibilities. There is an option here, there's no restriction here saying that we can't give one of the ninjas no stars. So there is a distribution where you give the first ninja 4 stars and the third ninja 3 stars. Or you could consider possibilities where you don't give the first 2 ninjas any stars and you give all of them to the third one. He's a star hog. So why this is often called stars and bars is because what we do is we pretend first that these are ordered bins, but then we get rid of the underline and the first and last line, and now you see what's called a star and bar chart. And the point is the bars serve as the dividers between different people. So you see there are 3 stars in the beginning before the first bar that tells you how many were in the first bin. You see 2 stars between the first bar and the second bar, that's how many are in the second bin. And finally you see 2 stars after the last bar, that's how many are in the third bin. And so you see if you do these types of diagrams, this case where someone got none corresponds to 2 bars being right next to each other. So if there's no stars between 2 bars, that person got none. And then finally, of course, this last one corresponds to all 7 stars being at the end. 5, 6, 7. So the bars serve as dividers, dividing the stars up between the different people. And so each star and bar chart corresponds to a different solution to this problem. Now granted, you do not want to solve this problem by listing all of these stars and bar charts because they take forever. But the point is, the way I've described it, you can see that you can go back and forth. Each distribution gives you a star and bar chart, and each star and bar chart gives you a distinct distribution. In the phrase notion of bijective combinatorics, there's a one-to-one correspondence between solutions to this problem in these pictures. And why would you do such a thing? Well, this star and bar chart, what is it? It's a string of 7 characters, or actually 9 characters. The 2 possible characters are either a star or a bar. So we're looking at a bit string of length 9 that has 7 stars in it. And we already know how to count those problems. It's counted by a binomial coefficient, 9 choose 7. Of course, in general, we want to replace 7 and 3 with any possible numbers. And so we see, as I change the 7, this changes the number of stars. As I change the number of people, this changes the number of bars. So in general, these bit strings, the number of bit strings, the length of the bit string is the sum of the stars and the bars, and then the number of stars is how you choose which occurrences are stars and which occurrences are bars. And you can look at this actually being as the same thing as a lattice path, in the sense that you could view the stars as going east and the bars as going north. But the reason why we make this distinction is because oftentimes you'll see there's a -1 going on. 3 becomes 2. And so it's always the number of stars plus the number of bars, choose the number of bars. But you should be careful. Usually in most of the word problems, the number of bars is the number of people -1. Now on to problem 2. Find the number of solutions to the equation x plus y plus z equals 12. Here I'm assuming x, y, and z are non-negative integers, because as you know, if I allow rational numbers, this answer becomes infinity, thanks to linear algebra. But if you do things with integers, the world of linear algebra falls apart and you have to do more work. One approach to solve these types of problems is to do a star and bar chart. And the idea is, well, x, y, and z are specific non-negative integers. Put x number of stars first. So for instance, 8, 3, and 1 is a possible solution to this equation. So put 8 stars first. Then where you see the plus sign, you put a bar. And then the next coordinate, the y, you put y stars. Then when you see the plus sign again, you put another bar. And then finally, you put the number of z stars. So this solution, 8, 3, 1, corresponds to 8 stars, a bar, 3 stars, a bar, and a star. And then when you look at it, you see how many stars must there be? Well, 8, 3, and 1 are x, y, and z, have to add up to 12, so there must be 12 stars. How many bars must there be? Well, it's the number of plus signs, also known as the number of variables minus 1. So you have that minus 1 bit going on here. And so you see, to each solution to this equation, you have a star and bar chart, and you can go backwards. Given the star and bar chart, the number of stars before the first bar is the first coordinate. The number of stars between the ith after the ith bar is the I plus first coordinate. And so that gives you the bijection. And so the number of solutions to this equation is 12 plus 2, choose 12, or 14, choose 12. Or, 14, choose 2, if you actually want to calculate this by hand. And then that would give you what? 21, 91 possible solutions. The third problem I'm going to look at has to do with Pokemon. So back in the day when I was a kid, there were only 150, so that's what I'm going to work with. How many Pokemon teams can you form with the first generation Pokemon? There's 150 to choose from. Of course, you all know you should choose Pikachu. And the number of Pokemon you usually have on a team is 6. As usual, there's always the question of whether or not order matters. For this purposes, I'm going to assume order doesn't matter, because if you've ever played Pokemon, you know that you can always swap out your team members in the middle of battle, so the order of the Pokemon doesn't actually matter. Well, how do you solve this problem? Well, you could turn it into a linear equation like on the previous problem. You let x sub 1 be the number of Bulbasaurs on your team, x sub 2 be the number of Venusaurs, x sub 3 be the number of, Ivysaurs. Man, I got it out of order. Oh well. All the way up to x150, that's Mewtwo, the number of Mewtwo's. In general, x sub I is the number of Pokemon in the ith entry in the Pokedex. In other words, if you've ever played Pokemon, each Pokemon species is given a unique number. And so the point is, your team is really a solution to the equation x1 plus ... plus x150 equals 6. So you have 150 variables. They're all non-negative integers, and they have to add to 6. Clearly, there's going to be a lot of zeros. But now you see the 6, and you realize, well, it's 6 stars again. There's 150 Pokemon, so there are 149 plus signs, so there's 149 bars. And so now with just using the star and bar chart argument, you see that the number of Pokemon teams is this. 149 plus 6 choose 6, which is 155 choose 6, which if you're crazy and you actually calculate, because you can, ends up being 17 billion different teams. I'm not going to lie, I tried this with the current number, and it ends up being a number so big that Google ends up having to use the E notation. So these numbers get big quickly, which is one reason why binomial coefficient notation is preferable. This is a much easier thing to write than this, and eventually when these numbers get big enough, you can't write the right-hand side anyways. So again, we see this problem involved picking Pokemon, and we found a clever way to turn it into stars and bars. There's actually a way to bypass this in general. The idea was that you'd have, if you had 0 Bulbasaurs, you'd have no stars before the first bar, and the number of stars before the first bar is the number of Bulbasaurs on your team, and then so on and so forth. So now that I've studied these three problems, I will generalize them and we'll talk about the more general setup and what the stars and bars formula gives you in each of those cases.